So chapter 14 is pretty similar to chemistry we've seen before in our addition chapter, but we're going to go over it in a lot more detail. But I did want to start off by reviewing some basic nomenclature and property of ethers. I am going to ask you to watch the nomenclature video at home or read through the textbook just because I don't want to waste a lot of class time on it. If you're interested in reading the textbook, it is section 14.2, or you can watch the online video. The online video is nice and short. It's from the Khan Academy, and it does a good job of explaining basic ether nomenclature. I don't expect you guys to know all of the wackadoodle funky ether names, but I did want to show you guys a couple of common ethers that don't really follow the IUPAC naming system. The first one does follow the IUPAC naming system, but I just wanted to cover it anyways. What's this solvent called? Diethyl ether. Looks like a bat. This is one of the most common ethers that you'll use as an organic chemist. It's really nice because it's very volatile, which means it evaporates very easy. It's a nice solvent to use, and we've used it in lab. All right, then we've got another ether that doesn't follow the IUPAC name, but it's also used commonly as a solvent. Does anybody know what this is called? Tetrahydrofuran. So unfortunately, when you get into these heterocyclic systems, the aromatic relative of this is called furan. And this one has 4 extra hydrogens on there that furan doesn't. So if we look at these blue protons, they're present in furan, but if we look at tetrahydrofuran, we're just adding on 4 new positions. And so unfortunately, when you get into a lot of these aromatic heterocycles, the naming systems get pretty convoluted. So this is just referred to as tetrahydrofuran. Exactly. So most people just refer to this as THF. And so we've seen this used quite a bit as a solvent. What reaction did we see it used as a solvent in? Yeah, hydroboration oxidation. And that has to do with the unique properties of ethers. They're really, really good at stabilizing Lewis acids. So I'm going to erase this for now, and then we'll talk about that in a second. What do you think is more polar, tetrahydrofuran or diethyl ether? What do you guys think? Why do you think THF?
Because there could be some resonance with furan.
Not quite. So if we try to do resonance structures with THF, we can't move those electrons around without violating an octet rule. What do you think?
The dipole is more organized. It's in a ring, so they're stuck in position. Whereas in diethyl ether, those ethyls can rotate around. So
exactly.
There's a more permanent dipole.
So if we look at THF, there's a permanent dipole. I like to think of diethyl ether as that wacky flailing arms guy you see at like car lots. It's out there flailing away. Where THF, they're basically locked behind, so it's constantly got this permanent dipole pointing towards the oxygen. It's a much, much, much more polar solvent than diethyl ether. And it makes a really good ligand. All right, there's one last one I wanted to talk about that's also got a non-IUPAC type name. And this is called 1,4-dioxane. This is really similar to THF. It's got a really strong permanent dipole pointed towards the oxygens. However, it's got a little bit less of an overall net dipole. And it's got a much, much higher boiling point. So there are some reactions where you actually need to crank up the heat a fair amount, but you still want to use an ether solvent. That's when you would use something like 1,4-dioxane.
You say it's less full?
So it does have strong dipoles towards each of the oxygens, but if you look at the net dipole, it's canceling out, kind of.
Okay, so it's less overall.
Yes, exactly. So it's really utilized when you want to have an ether solvent with a high boiling point, but some polarity, just not a ton of polarity. Yeah. So these are the non-standard common ethers. And let's take a look at why we use ethers. So the first one we saw is that it's a common solvent. The other nice thing that I mentioned briefly is that they can be weak Lewis bases. And so we saw in our example of BH3-THF that we had these borane molecules where we had this big old empty p orbital, which makes it quite unstable. And so anytime you've got an ether solvent nearby, one of these lone pairs will actually just get pushed into this empty p orbital and help stabilize it through a Lewis acid-base adduct. They're really, really nice at doing that. All right, the other thing that's nice about these is that they're fairly inert. What does it mean when I say inert? Yeah, or not reactive. Which makes them really good as ligands or as solvents, right? You don't want your solvent to necessarily react in your reaction that you're doing. The other thing, too, that makes it kind of nice is that it's a good H-bond donor, or acceptor. So if you remember, if you've got some sort of group that has a hydrogen bond donor, which would be this guy right here, that an ether, in this case, can basically be a lone pair donor. And I'm just going to draw two generic R groups where it is really, really strongly attracted to any sort of hydrogen bond. That means that you oftentimes see ether functional groups in a lot of designer drugs or just pharmaceutical drugs in general, is that they're really good at stabilizing hydrogen bonds. All right, so now we've got to change gears a little bit and talk about the non-generic ethers. These are called the epoxides. And I totally ripped this off of another guy's website. He calls epoxides the black sheep of the ether family. So you can see the kid in the corner surrounded by this very generic vanilla family. They look pretty inert. He looks very, very reactive. So epoxides are super duper reactive ethers. And these make really good intermediates. So in general, we don't want our intermediates to be too inert, or else we have to do a lot of fancy stuff to get them to react and form a new functional group. But with ethers, or with epoxides, we're really set. And so let's take a look at our generic epoxide. So let's say I've got ethylene here, and I want to make an epoxide. What sort of reagent would I need? I'm going to move this up. Does anybody remember?
Peroxy acid.
Yeah, we need a peroxy acid, exactly. So the most common peroxy acid that we're going to use for forming an epoxide is MCPBA. And we said that this is going to be super duper reactive because of what?
D ring.
What's
Yeah,
that?
Stable ring.
Yeah, it's a 3-membered ring. We said 6-membered rings are far and away the most stable. This is like a mousetrap waiting to go off. Essentially, all you need is some sort of nucleophile to hit one of those carbons, and it will slingshot open really, really quickly. So this is unstable due to ring strain. But the nice thing with it is it's stable enough to isolate. So you can actually isolate an epoxide, carry it on to your next step, and then have it react with your next nucleophile. There are a handful of other cyclic ethers. However, we're really not going to get into them too much, but I did want to briefly show you them. So I'll write other less common cyclic ethers. And these would be things like oxetanes that are the 4-membered rings. These really aren't used that commonly in organic synthesis because they're less reactive, they're harder to make. You can also have oxalanes. Oops. Oop. And you can have a bunch of other ones of varying ring sizes. However, epoxides far and away are the most common, and we're going to spend a chunk of time talking about them.
Wasn't that THF?
Yeah, the THF is the formal name for this. Anytime you see a 5-membered ring with oxygen, the overall functional group is called an oxalane. Yeah, that's a good point. Kind of like when we say aldehyde, it doesn't mean the overall molecule will be called an aldehyde. THF is the formal name. Yeah. All right, before we get into reactivity, though, I get to talk about chemistry I like. And these are crown ethers. Have you guys talked about these at all in your other classes?
I've heard.
They're really, really interesting, and my entire PhD was based on supramolecular chemistry, which is really rooted in a lot of this sort of chemistry. So let's draw out some of these crown ethers. This crown ether has 4 oxygens and 8 carbons in there. This is called 12 crown 4. Pretty interesting stuff. You can buy it. It's not super expensive. The other one that we have has 5 oxygens. So you can kind of space out your oxygens, and they've got 2 carbon linkers connecting them all. And this is called 15 crown 5. And then last but not least, we've got 18 crown 6, where we've got 6 oxygens instead of 5. In fact, I'm going to blow this up a little bit more. And in the 60s, everybody was doing a lot of cool chemistry with these crown ethers. So this is 18 crown 6. In fact, there were a couple of Nobel Prizes awarded to the chemists that were working on these crown ethers. And a lot of these were derived from nature. So I've got this pseudo crown ether drawn below. And this is a really cool drug called vanillamycin. And what they notice with vanillamycin is that it binds potassium ions really, really well. In fact, it binds potassium ions 1,000,000 times more tightly than sodium. And so you can imagine if you're a potassium ion, you could just kind of snuggle into the center portion here, and all of a sudden you've got interactions with all of these oxygens. So they're all donating some electron density towards this electron deficient cloud of the potassium. Why do you think sodium doesn't bind as tightly?
It's smaller, so it doesn't reach as well.
Yeah, it's a lot smaller. So in this case, the idea was nature does a really, really good job of designing molecules of a specific size and shape. You guys have talked about this a lot in your bio classes with enzymes, right? Can we do this synthetically in the lab? And the answer was absolutely. If we look at 18 crown 6, this binds potassium super duper well because it's the appropriate size, and the crown ether will essentially wrap up that potassium ion. What do you think 15 crown 5 could bind?
Sodium and
Sodium. Potassium is actually too big to bind very well in there. So they're able to have these sodium ions snuggle in. And then 12 crown 4? Lithium. And you might be thinking, okay, who cares, right? But I'll show you guys some cool reactions that are based off of this. So let's say I've got this alkyl halide, and I react this with potassium fluoride, so KF. We would think, hey, this could do SN2 chemistry, and I could get a fluorine installed on there, right? Wrong. This will not work. Does anybody know why this will not work very well? Well, one of the main reasons is that potassium fluoride has tight ion pairing. Because that fluorine is so electronegative, it desperately wants to stay close to that potassium, which makes it a pretty crummy nucleophile. That's why in first term I told you guys you really never see fluorine act as a nucleophile. However, a cool trick is that if you take potassium fluoride, you could use a crown ether solvent. Which crown ether solvent would we want to use?
Vanillamycin.
Vanillamycin, you could. But it'd be a lot cheaper and easier to use 18 crown 6, and now all of a sudden you've got access to substitution chemistry involving fluorines. So supramolecular chemistry is becoming more and more useful for organic transformations. You don't see a lot of it in our textbook. However, the big new thing in chemistry is coming up with supramolecular catalysts. So if you guys have seen the catalysts that we've been using in lab, most of them are metal-based, right? Metals, for the most part, aren't environmentally friendly. They're hard to make. They're expensive. However, the organic supramolecular catalysts are dirt cheap. They're basically trying to mimic biological systems like with these crown ethers, and they're widely available. So instead of relying on a really expensive ruthenium catalyst, you could rely on something that's maybe a couple bucks for 100 grams. So this is becoming really big chemistry, and I like to talk about this every year just because it's up my alley. Sound good? All right. So let's talk about one last reaction, because this one's super easy, and this is preparation of ethers, and I'll go over the industrial method first. And with the industrial method, this only works for small, simple ethers. So the first thing you do is you get a generic alcohol, like ethanol. And if we treat this with acid, some super duper strong acid, first thing that will occur is we'll protonate our alcohol, right? Now our alcohol is a good leaving group. And if you've got more of your ethanol around, ethanol is a weak enough nucleophile to do a backside attack and basically do SN2 style chemistry. And then last but not least, you would have some sort of aqueous workup where this water can come steal this proton back and give you your neutral diethyl ether. However, the really big downside to this sort of industrial preparation is it requires really, really high temperature, and it requires super duper strong acid. So if you've got any other functional groups on your molecule, it can tend to cook those functional groups. So if you've got an alkene, for example, you get unwanted addition reactions. However, this does work really well for simple ethers, and it's got pretty high atom economy, and it's fairly green. The other method that's used is the Williamson ether synthesis. And this one you guys actually know, but we're calling it a new fancy name now. And that is, if you've got some sort of alcohol, just treat it with a strong base like sodium hydride. Now you've got an alkoxide. And then all you need to do is react this with some sort of molecule with a leaving group on it. And voila, you've created your ether pretty easily. However, this obviously isn't as environmentally friendly because it's 2 steps. However, it's a little bit more rugged and reliable compared to the reaction with super duper strong acid. So it's a good approach. All right, when we come back tomorrow, we're going to talk about a lot of other chemistry, and we're going to do some review of our epoxide reactions.